So, here's something worth thinking about as you settle in tonight. Right now, wherever you are, there are particles of light hitting your skin. Trillions of them, every second, just washing over you like rain you can't feel. And each one of those tiny packets of light is doing something that, if you really sit with it, is one of the strangest things in all of science. Each one is behaving as both a wave and a particle at the same time, not switching between the two, not sometimes one and sometimes the other, both, always. And nobody, not Einstein, not Feynman, not any physicist alive today, can fully explain why. They can describe it beautifully with mathematics. They can predict it with astonishing precision. But explain it in the way you'd explain why a ball rolls downhill? No, not really. And that's quantum mechanics. It's the most successful, most precisely tested theory in the history of science, and at its heart, it contains ideas that feel like they shouldn't be true. Ideas that the people who discovered them didn't want to believe. Ideas that started arguments lasting decades, ended friendships, and forced an entire generation of physicists to rethink what it means to understand anything at all. But here's the thing, quantum mechanics didn't arrive all at once. It wasn't a single eureka moment. It was built slowly, piece by piece, over about 30 years, by a handful of people who were mostly just trying to solve very specific, very practical problems. Problems about light, problems about heat, problems about why certain metals glow certain colors when you heat them up. And the answers they found were so strange, so uncomfortable, that many of them spent the rest of their lives trying to undo what they'd discovered. That's the story I want to tell you tonight. How we got here, how these ideas were assembled, and why. Once you understand the history, the weirdness of quantum mechanics starts to feel less like magic and more like the universe gently insisting that reality is deeper than our everyday intuitions can reach. Let's start where it actually started, which is with a problem about ovens. Seriously. Ovens. It was the late 1890s, and physicists in Germany were obsessed with something called blackbody radiation. Now, that sounds technical, but the idea is beautifully simple. Imagine you have a hollow metal box, like a kiln or a furnace, and you heat it up. As it gets hotter, it starts to glow, first a dull red, then orange, then yellow, then eventually white-hot if you push it far enough. You've seen this with a stovetop burner or a piece of iron in a blacksmith's forge. The color changes as the temperature rises. And the question physicists were asking was, can we predict exactly what colors of light, what wavelengths, this glowing box will emit at any given temperature? Can we write down an equation that perfectly describes the spectrum of light coming out of a heated object? This wasn't just an abstract puzzle. Germany in the 1890s was industrializing rapidly, and there were very practical reasons to care about this. The German Bureau of Standards, a government agency called the Physikalisch-Technische Reichsanstalt, was actually funding this research partly because the lighting industry needed better standards. If you're manufacturing light bulbs and gas lamps, you need to understand how hot materials produce light. So there was money behind this question, which meant some of the best experimental physicists in the world were carefully measuring the exact spectrum of light coming out of precisely controlled heated cavities. And their measurements were excellent. Beautifully precise data, clean curves, everything you could want. The problem was that nobody could explain the data. The existing theories of physics, classical physics, the physics of Newton and Maxwell and Boltzmann, predicted something catastrophically wrong. Here's what I mean. According to classical physics, when you calculate how energy should be distributed among all the possible wavelengths of light inside a heated cavity, you get a prediction that works pretty well for long wavelengths, the red and infrared end of the spectrum. But as you move to shorter wavelengths, toward the ultraviolet, the classical prediction doesn't just drift a little off. It goes to infinity. The theory says that a heated object should emit infinite energy at short wavelengths. Infinite. Which is obviously absurdly wrong. Your oven does not emit infinite ultraviolet radiation. You would notice. This was such a dramatic and embarrassing failure that it got a name, the ultraviolet catastrophe. And it wasn't a small error or a missing correction term. It was a fundamental breakdown. Classical physics was saying something that was flatly impossible, and no amount of clever tweaking could fix it. Now, several physicists took runs at this problem. Lord Rayleigh and James Jeans in England had derived the formula that produced the catastrophe. Wilhelm Wien in Germany had come up with a different formula that worked well at short wavelengths but failed at long ones. So you had two formulas, each right in its own domain, and neither one could describe the whole picture. It was like having two different maps of the same city, and they didn't agree on where the streets were. Enter Max Planck. And here's where I want you to really picture this man, because he's one of the most fascinating figures in the history of physics, and his personality matters to this story. Planck was born in 1858 in Kiel, Germany. He was, by all accounts, deeply conservative, not politically, but intellectually. He loved order. He loved classical physics. He believed in absolute laws of nature, in thermodynamics as a kind of sacred edifice. He was not the kind of person who would cheerfully tear down the foundations of physics. He was the kind of person who would try every possible conventional solution before even considering something radical. And that's exactly what makes what happened next so remarkable. By the fall of 1900, Planck had been wrestling with the blackbody problem for years. He knew Wien's formula, which worked at short wavelengths. He knew the Rayleigh-Jeans formula, which worked at long wavelengths. And on October 19th, 1900, we actually know the date, he presented a new formula to the German Physical Society, a formula he'd essentially guessed, or more accurately, interpolated. He'd found a mathematical expression that smoothly connected the two regimes, that matched the experimental data across the entire spectrum. And it worked. It matched the data perfectly. The experimentalists checked it that very night, and the next morning, one of them, Heinrich Rubens, called Planck to tell him the formula was exact. But here's the thing. Planck had the formula, but he didn't know why it worked. He had the right answer, but no derivation, no physical explanation. And that bothered him enormously. So over the next 2 months, he worked backward, trying to find a theoretical justification for his formula. What assumption would he need to make about the physics of the situation to derive this equation from first principles? And what he found disturbed him. The only way to make the math work, the only way to derive his formula, was to assume that energy is not continuous. Let me explain what that means, because it's the key to everything. In classical physics, energy is smooth. It flows like water. You can have any amount of it. 1.0 units, 1.001 units, 1.0000001 units. Anything. Energy is infinitely divisible, like a number line. But Planck found that to get his formula, he had to assume that the atoms in the walls of the cavity could only emit or absorb energy in discrete chunks, specific amounts. Not any amount, but only whole number multiples of some tiny basic unit. He called these chunks quanta, from the Latin word for how much. And the size of each quantum wasn't arbitrary. It depended on the frequency of the light. Higher frequency light, bluer light, ultraviolet light, came in bigger chunks. Lower frequency light, redder light, infrared, came in smaller chunks. The relationship was simple and elegant. The energy of one quantum equals the frequency of the light multiplied by a constant. A very, very small constant. A number so tiny that in everyday life you'd never notice the chunkiness. Planck called it h. We call it Planck's constant. Its value is about 6.626 times 10 to the negative 34 joule-seconds. That's a decimal point followed by 33 zeros and then a 6. Unimaginably small, but not zero. And that makes all the difference. Think about it this way. Imagine you're on a ramp versus a staircase. On a ramp, you can stand at any height. It's continuous, smooth. On a staircase, you can only stand on specific steps. In everyday life, energy looks like a ramp, but Planck was saying that at the atomic level, energy is a staircase. The steps are just so incredibly tiny that you can't tell the difference in normal experience. But when you're dealing with individual atoms and high-frequency light, those steps matter. And the ultraviolet catastrophe? It goes away because at high frequencies, the energy steps become so large that atoms can't easily climb them. It's like the staircase suddenly has steps that are 10 feet tall. Almost nothing can get up there. So the amount of energy emitted at those high frequencies drops off, exactly as the experiments showed, instead of shooting off to infinity. Now here's what's really important about Planck's state of mind. He did not think he had discovered something fundamental about nature. He thought he'd used a mathematical trick, a computational device. He assumed that someone, eventually, would find a way to derive the same formula using purely classical physics, and the whole business about energy quanta would turn out to be a convenient fiction. He called it an act of desperation. Those are his actual words. Years later, he wrote that it was an act of desperation because a theoretical explanation had to be found at any cost, whatever the price. He was deeply uncomfortable with what he'd done, and he spent years afterward trying to undo it, trying to find a classical explanation. He never found one. And this is something I think is worth sitting with for a moment. The man who started the quantum revolution didn't want it, didn't believe in it really. He was a conservative thinker who stumbled onto something radical while trying to solve a practical problem about how hot things glow. He was 52 years old in 1900, already a respected professor, not some young rebel looking to overthrow the establishment. He was the establishment. And the idea that energy comes in discrete packets, this idea that would eventually reshape all of physics, was, to him, a desperate mathematical patch that he hoped would be temporary. But it wasn't temporary, because 5 years later, in 1905, a 26-year-old patent clerk in Bern, Switzerland, picked up Planck's idea and ran with it in a direction that Planck himself would never have gone. And this young man, you already know his name, was Albert Einstein. And what Einstein did with the quantum idea in 1905 was, in some ways, even more radical than what Planck had done. Because Planck had said that atoms emit and absorb energy in chunks. That's a statement about atoms, about matter. Einstein said something much bolder. He said the light itself comes in chunks. That light isn't just a wave, it's also made of particles, little bullets of energy, each one carrying exactly one quantum of energy, exactly h times the frequency. And he didn't propose this just as an abstract theory. He used it to explain a specific, stubborn experimental puzzle, something called the photoelectric effect. And the story of how that worked, and why it was so convincing, and why it made almost everyone uncomfortable for the next 20 years, is one of those beautiful moments in science where a single clean idea cuts through decades of confusion. The photoelectric effect had been discovered back in 1887 by Heinrich Hertz, the same Hertz whose name we use for frequency, cycles per second. Hertz had noticed that when ultraviolet light shines on a metal surface, the metal emits electrons. It kicks them right out of the surface. And that by itself wasn't so surprising. Light carries energy, and if you dump enough energy into a metal, maybe electrons can escape. But the details were baffling. Because the energy of the ejected electrons didn't depend on how bright the light was. You could shine a very dim ultraviolet lamp on the metal, and the electrons that came out were just as energetic as with a bright lamp. There were fewer of them, sure, but each individual electron had the same energy. And if you used red light instead, even incredibly bright red light, blindingly intense, no electrons came out at all. None. No matter how long you waited, no matter how much red light you poured onto the surface. Classical wave theory couldn't explain this. If light is a smooth, continuous wave, then a brighter wave carries more energy, and eventually that energy should be enough to knock electrons loose, regardless of color. But that's not what happened. And Einstein realized that if light comes in particles, if each particle carries an energy determined by its frequency, then everything falls into place. A single photon of ultraviolet light carries enough energy, because ultraviolet has a high frequency, to knock an electron free. One photon hits one electron, and if that photon's energy exceeds the amount needed to pry the electron loose from the metal, out it goes. The leftover energy becomes the electron's kinetic energy, its speed. That's why dim ultraviolet light still produces fast electrons. Each individual photon still packs the same punch. You just get fewer electrons because there are fewer photons arriving. And red light? Red light has a lower frequency. Each red photon carries less energy, and if that energy falls below the threshold needed to liberate an electron, it doesn't matter how many red photons you throw at the surface. None of them, individually, have enough energy to do the job. 1,000 weak punches don't add up to one strong one. Not in this case. Each photon acts alone. Einstein wrote this up in a paper in 1905, the same miraculous year he published Special Relativity and his work on Brownian motion. And here's something worth noting. When Einstein eventually won the Nobel Prize in 1921, it wasn't for relativity. It was for this, for the photoelectric effect, for explaining how light behaves as particles. That tells you something about how important this idea turned out to be, and also, honestly, about how controversial relativity still was at the time. The Nobel Committee felt safer rewarding the photoelectric work, which had clear experimental confirmation. But don't think for a second that Einstein's light quantum idea was warmly received. It wasn't. Most physicists thought it was, at best, a useful fiction. Even Planck, the man who had introduced quanta in the first place, resisted the idea that light itself was actually made of particles. Planck had treated quantization as something that happened at the point of emission, at the surface of the glowing body. He thought the restriction was about how matter emits and absorbs energy, not about the nature of light in flight. Light, once released, was still a wave. Had to be. Because the wave theory of light was one of the most successful theories in all of physics. It explained interference, diffraction, polarization. Beautiful, precise predictions confirmed by a century of experiments. You don't throw that away because of one clever paper by a patent clerk in Bern. And honestly, their caution was reasonable. The evidence for light as a wave was overwhelming. Thomas Young's double-slit experiment, way back in 1801, had shown light creating interference patterns. Bright and dark bands that only make sense if light is a wave, with crests and troughs that can reinforce or cancel each other. Maxwell's equations, from the 1860s, had unified electricity and magnetism and predicted electromagnetic waves that traveled at exactly the speed of light. The match was too perfect to be coincidence. Light was an electromagnetic wave. Case closed. Except now Einstein was saying, well, also particles. Both. Somehow. This is the tension that would haunt physics for the next 2 decades, and in some ways, it's never fully gone away. Light behaves like a wave when you test for wave properties. It behaves like a particle when you test for particle properties. And the natural question, okay, but what is it really? Turns out to be the wrong question. Or at least, it's a question that quantum mechanics eventually answers in a way that nobody finds entirely satisfying. But we'll get there. For now, let's stay in the early 1900s, because something else was happening that would prove just as revolutionary. While Einstein was rethinking light, other physicists were trying to figure out the structure of the atom itself, and the quantum ideas that Planck and Einstein had introduced for light were about to invade matter in the most unexpected way. The story starts with Ernest Rutherford, a New Zealander working in England, one of the great experimentalists of all time. Big personality, booming voice, hands-on in the lab in a way that many theoretical physicists of the era were not. In 1911, Rutherford and his colleagues Hans Geiger and Ernest Marsden performed one of the most famous experiments in physics. They fired tiny, fast-moving alpha particles, which are basically helium nuclei, little bundles of positive charge, at a thin gold foil. The expectation, based on the prevailing model of the atom, was that the alpha particles would pass through with only slight deflections. The atom at that time was imagined as a sort of diffuse blob of positive charge with electrons embedded in it, like raisins in a pudding. J.J. Thomson's plum pudding model. And if the positive charge is spread out evenly throughout the atom, there's nothing dense enough to seriously deflect a fast-moving alpha particle. Most of the alpha particles did pass straight through, but some of them bounced back. Not just deflected a little, bounced back toward the source. Rutherford later said it was as if you fired a cannon shell at tissue paper, and it came back and hit you. That result was shocking. And Rutherford realized the only way to explain it was if almost all the mass and positive charge of the atom was concentrated in a tiny, dense core, a nucleus, with the electrons orbiting far away, like planets around a sun. The atom was mostly empty space. Now, this was a triumph of experimental physics, but it immediately created a devastating theoretical problem. And this is where quantum mechanics enters the story of matter, not just light. Here's the issue. According to classical electrodynamics, Maxwell's equations, the very same equations that so beautifully described light, an electron orbiting a nucleus should continuously radiate energy. It's an accelerating charge because circular motion involves constant acceleration toward the center, and accelerating charges emit electromagnetic radiation. That's how antennas work. So the orbiting electron should be constantly losing energy, spiraling inward, radiating across a continuous spectrum of frequencies as it goes, and within a tiny fraction of a second, we're talking about 100 millionth of a second, it should crash into the nucleus. The atom should collapse almost instantly, But atoms don't collapse. They're stable. You're made of them. The chair, the bed, the walls around you, all made of atoms that have been perfectly stable for billions of years. So something was deeply, fundamentally wrong with the classical picture. This is where Niels Bohr enters. And Bohr is one of those figures you really need to spend some time with, because his fingerprints are all over quantum mechanics. He was Danish, born in Copenhagen in 1885, son of a physiology professor. He was a soccer player, actually quite good, though his brother Harold was better, good enough to play for the Danish Olympic team. Bohr was known even as a young man for his deep, slow, careful way of thinking. He would agonize over every word in a paper, revising drafts endlessly, driving his collaborators slightly mad. But when he arrived at a conclusion, it tended to be profound. In 1913, Bohr proposed a model of the hydrogen atom that was, frankly, a strange hybrid. He took Rutherford's nuclear atom, electrons orbiting a central nucleus, and he simply declared, by fiat almost, that certain orbits were special, stable, allowed. In these specific orbits, and only these orbits, the electron would not radiate energy. It would just orbit, happily, indefinitely. He couldn't fully explain why these orbits were stable. He essentially postulated it. But the rule he used to determine which orbits were allowed was directly borrowed from quantum ideas. He said the angular momentum of the electron, a measure of how much rotational motion it has, must come in whole number multiples of Planck's constant divided by 2 pi. Quantized, discrete. Only certain values allowed, like rungs on a ladder. And here's what's really clever about this. When an electron jumps from a higher orbit to a lower one, it loses energy. And that energy is emitted as a single photon, a quantum of light, whose frequency is determined by the energy difference between the two orbits. The bigger the jump, the higher the frequency of the emitted light. And when Bohr calculated what frequencies of light hydrogen atoms should emit based on this model, he got numbers that matched the known spectral lines of hydrogen with extraordinary precision. These spectral lines, specific, sharp colors of light that hydrogen emits when heated, had been measured decades earlier by Johann Balmer and others, and they followed a mysterious numerical pattern that nobody could explain. Bohr's model explained them. The pattern fell out of the math naturally. Think about what that means. For decades, scientists had known that each element emits its own unique set of colors, like a fingerprint. Heat sodium, you get that distinctive yellow-orange glow. It's why sodium streetlights have that particular color. Heat hydrogen, you get a specific set of lines: red, blue-green, violet. These were cataloged, tabulated, used practically in spectroscopy. But nobody knew why. Why those particular colors? Why not a smooth, continuous rainbow? Bohr's model answered this in one stroke. Atoms emit specific colors because electrons can only occupy specific energy levels. Each color corresponds to a jump between two levels. The spectrum is discrete because the energy levels are discrete. Because the underlying physics is quantized. It was a stunning success. But it was also, everyone recognized, a deeply unsatisfying theory. It worked beautifully for hydrogen. One electron, one proton, the simplest atom. But when you tried to extend it to helium, with 2 electrons, it broke down. The predictions didn't match, and the whole thing rested on these arbitrary rules. Electrons can only be in certain orbits. They don't radiate when they're in those orbits. They jump instantaneously between orbits without passing through the space in between. Why? Bohr couldn't say. He had grafted quantum rules onto a classical picture, and the seams showed. Still, the Bohr model was enormously influential. It established the idea that quantum conditions govern the internal structure of atoms. It showed that Planck's constant wasn't just relevant to thermal radiation or the photoelectric effect. It was woven into the fabric of matter itself. And it raised a question that would consume the next generation of physicists. If these quantum rules are real, if energy levels are truly discrete, if electrons really do jump between states without traversing the space between them, then what kind of theory could possibly explain all of this in a coherent, unified way? The answer would take another decade to arrive, and it would come from an unexpected direction. Because the next great insight didn't come from thinking harder about particles. It came from a French prince with a wild idea about waves, an idea so audacious that his doctoral thesis committee wasn't sure whether it was brilliant or completely insane. His name was Louis de Broglie, and in 1924 he submitted a doctoral dissertation at the University of Paris that would turn physics inside out. De Broglie came from an aristocratic family. The de Broglie family held a hereditary dukedom, and Louis himself would eventually inherit the title. He'd originally studied history, actually, before switching to physics, partly inspired by his older brother Maurice, who was doing experimental work with X-rays. And here's this young aristocrat, not yet established in the field, sitting down and asking what might be the most beautifully simple question anyone had asked in a generation. If light, which everyone thought was a wave, turns out to also behave like a particle, then shouldn't matter, which everyone thinks is made of particles, also behave like a wave? Just sit with that for a second. It's one of those ideas that sounds either profound or ridiculous depending on your mood. Einstein had shown that light waves carry momentum in discrete packets, photons. De Broglie essentially ran the logic in reverse. He said, okay, if a photon has a wavelength related to its momentum by Planck's constant, specifically wavelength equals h divided by momentum, then why can't we write the same equation for an electron, or a proton, or a baseball for that matter? Every moving particle, de Broglie proposed, has an associated wave, and the wavelength of that wave is Planck's constant divided by the particle's momentum. The faster and heavier the particle, the shorter the wavelength. The lighter and slower it is, the longer the wavelength. Now, the reason you don't notice wave behavior when you throw a tennis ball is that the ball's momentum is enormous compared to Planck's constant, which is absurdly tiny, 6.6 times 10 to the negative 34 joule seconds. So the wavelength of a tennis ball in flight is something like 10 to the negative 34 meters. That's not just small. That's so far below the size of an atom, so far below the size of a proton, so far below anything measurable that it's effectively zero. The wave nature of a tennis ball is real in principle, but utterly invisible in practice. But an electron? An electron is incredibly light. And when it's moving at the kinds of speeds electrons move at inside atoms, its de Broglie wavelength turns out to be roughly the size of an atom, which means the wave nature of an electron isn't some negligible footnote. It's the dominant feature of its behavior at atomic scales. And here's what's really beautiful about this. Remember how Bohr's model had those quantized orbits? Those specific allowed energy levels that electrons could occupy, and nobody could explain why? De Broglie's wave idea gave a reason. Think of it this way. Imagine wrapping a wave around a circle, like a vibrating string bent into a ring. If the circumference of that ring is exactly a whole number of wavelengths, the wave reinforces itself. It fits perfectly. You get a stable standing wave, like the harmonics on a guitar string. But if the circumference is not a whole number of wavelengths, the wave interferes with itself destructively. It cancels out. It can't sustain itself. So de Broglie said, the reason electrons can only exist in certain orbits is that only certain orbits allow the electron's matter wave to form a stable standing wave around the nucleus. The quantization isn't some arbitrary rule imposed from outside. It's a natural consequence of the wave nature of matter. Bohr's allowed orbits are simply the orbits where the electron wave fits. That's gorgeous. That's the kind of insight that makes you want to sit back and just appreciate the elegance of it. And when de Broglie worked out the math, the condition for a standing wave, that the circumference equals a whole number of wavelengths, turned out to reproduce exactly Bohr's quantization condition for angular momentum. It wasn't just a hand-wavy analogy, the numbers matched. But his thesis committee, which included some serious physicists, was skeptical. The story goes that they weren't sure what to make of it. The idea was so novel, so speculative, that they sent a copy to Einstein for his opinion. And Einstein, to his credit, recognized it immediately for what it was. He reportedly said that de Broglie had lifted a corner of a great veil. The committee awarded the doctorate, and de Broglie would win the Nobel Prize in 1929. But in 1924, it was still just a theoretical proposal. Nobody had actually observed an electron behaving like a wave. That changed in 1927, and the experiment that confirmed de Broglie's hypothesis is one of those wonderful stories where the discovery was partly accidental. Clinton Davison and Lester Germer, working at Bell Labs in New York, were firing electrons at a nickel target and measuring how they scattered. During one experiment, a glass tube broke. The nickel sample got contaminated and oxidized, and to clean it, they heated it to high temperatures. What they didn't realize was that the heating process caused the nickel to recrystallize into large, orderly crystal domains. When they resumed the experiment with this accidentally recrystallized nickel, they found something completely unexpected. The scattered electrons showed a diffraction pattern. The electrons were diffracting off the crystal lattice of the nickel exactly the way X-rays diffract off crystals. And diffraction is a wave phenomenon. You can't explain it with particles bouncing around like little billiard balls. The electrons were behaving as waves, and the wavelength matched de Broglie's prediction precisely. Around the same time, independently, George Paget Thomson, the son of J. Thomson, who had discovered the electron as a particle in 1897, demonstrated electron diffraction by passing electrons through thin metal foils. There's a delicious irony there that people love to point out. The father won a Nobel Prize for showing the electron is a particle, and the son won a Nobel Prize for showing the electron is a wave. Both were right, which tells you something about how strange this new physics was becoming. So by the late 1920s, the situation was this. Both light and matter exhibited wave-particle duality. Light, long understood as a wave, also came in particle-like quanta. Electrons, long understood as particles, also propagated as waves. Planck's constant was the bridge between the two descriptions. It connected a particle's momentum to its wavelength and its energy to its frequency. And the whole framework was crying out for a unified mathematical theory that could handle all of this coherently. Two such theories arrived almost simultaneously, and the story of how they emerged and how they turned out to be secretly the same theory is one of the great dramas of 20th century physics. The first came from a young German physicist named Werner Heisenberg, and the way he arrived at it was almost aggressively abstract. Heisenberg was in his early 20s, working with Max Born in Göttingen, and also spending time with Bohr in Copenhagen. He was brilliant, intense, and philosophically radical. His approach was to say, stop trying to picture what's happening inside the atom. Stop trying to imagine little electrons orbiting like planets. We can't see orbits. We can't measure orbits. All we can actually observe are the frequencies and intensities of the light that atoms emit and absorb. So let's build a theory that deals only with observable quantities. In the summer of 1925, Heisenberg was on the island of Helgoland in the North Sea, recovering from a terrible bout of hay fever. His face was so swollen he could barely see. And there, working through the night, he constructed a new mathematical framework. Instead of describing an electron's position as a function of time, the way classical physics would, he arranged the observable quantities into arrays of numbers, tables of numbers, where each entry corresponded to a transition between two energy states. He wasn't thinking of these as matrices actually. He essentially reinvented matrix algebra without knowing that's what he was doing. When he multiplied two of these arrays together, he discovered something disturbing. The order of multiplication mattered. A times B did not equal B times A. In mathematics, that's called non-commutativity. And in everyday arithmetic, it doesn't happen. 3 times 5 is the same as 5 times 3. But in Heisenberg's quantum mechanics, the order in which you multiplied these arrays of physical quantities gave different results. Heisenberg found this deeply unsettling. He later recalled that when he first realized the math was working, that his strange, abstract scheme actually reproduced the correct energy levels of the hydrogen atom. He was so excited he couldn't sleep. He went out and climbed a rock on Helgoland and watched the sun rise. He was 23 years old. When he brought his work back to Göttingen, Max Born recognized the mathematical structures immediately. They were matrices, objects from a branch of mathematics that physicists at the time rarely used. Born, along with his student Pascual Jordan, helped formalize Heisenberg's scheme into what became known as matrix mechanics. It was rigorous. It was powerful. It gave correct predictions, and it was almost impossible to visualize. There was no picture of what was happening. No orbits, no trajectories, no waves. Just arrays of numbers obeying algebraic rules, and out popped the right answers. Most physicists found it deeply unintuitive, almost alienating. It felt like the math was telling you something profound about nature, but it refused to draw you a picture. And then, just months later, an entirely different approach appeared, one that was far more intuitive, far more visual, and far more comfortable for physicists trained in classical methods. It came from an Austrian physicist named Erwin Schrödinger, and the contrast between his theory and Heisenberg's could hardly have been sharper. Where Heisenberg had thrown out all attempts at visualization and worked in pure abstraction, Schrödinger built a wave equation, a beautiful, continuous differential equation that described how a quantum wave, what he called the wave function, evolves through space and time. If Heisenberg's approach felt like pure algebra, Schrödinger's felt like classical physics in a new dress. Physicists could use the familiar tools of calculus, partial differential equations, boundary conditions, all the machinery they'd spent years mastering. And when Schrödinger solved his equation for the hydrogen atom, he got exactly the same energy levels that Bohr had found, that Heisenberg had found, but now they emerged naturally from the mathematics of wave behavior. The quantized energy levels appeared as the natural frequencies of the wave function, the same way a violin string can only vibrate at certain frequencies determined by its length and tension. The physics community, by and large, breathed a sigh of relief. Schrödinger's approach was something they could work with, something they could picture. But there was an immediate and deeply troubling question lurking inside it, a question that Schrödinger himself struggled with for the rest of his life. The wave function, this mathematical object at the heart of his equation. What was it? physically. What was waving? For a sound wave, the air pressure oscillates. For a water wave, the surface of the water moves up and down. For an electromagnetic wave, electric and magnetic fields oscillate. But the quantum wave function, what substance, what medium, what physical quantity was it describing? Schrödinger initially hoped it represented something concrete, maybe the smeared-out charge density of the electron itself, as if the electron were literally spread through space, like a cloud. But that interpretation ran into problems almost immediately, and the person who offered the interpretation that stuck, the one we still use today, the one that opens up the deepest rabbit hole in all of quantum mechanics, was Max Born, back in Göttingen. And what Born proposed was something that nobody was entirely comfortable with, least of all Schrödinger. What Born proposed was that the wave function doesn't describe anything physical at all, not directly. It doesn't tell you where the electron is. It tells you the probability of finding the electron somewhere if you look. More precisely, the square of the wave function's magnitude at any point in space gives you the probability density of detecting the particle at that point. Not the charge density, not the mass distribution, not some smeared-out physical substance, just probability. Pure, abstract, mathematical probability. Let that sink in for a moment. The most fundamental equation in quantum mechanics, the one that governs the behavior of every particle in the universe, doesn't tell you what's happening. It tells you what might happen and how likely each possibility is. The electron isn't smeared out like a cloud. It's that our knowledge of where it is before we measure it is described by this wave of probability. And when we do measure it, when we actually look, we find the electron at one definite spot. The wave function doesn't gradually condense, it snaps. The probability of finding the electron at one location jumps to 100%, and everywhere else drops to 0, instantaneously. Born called this the collapse of the wave function, and it's one of the strangest ideas in all of science. Born published this interpretation in 1926, and it's worth noting that his paper was remarkably modest about it. He almost tucked it into a footnote. He was working on scattering problems, how particles bounce off other particles, and he needed a way to interpret the solutions Schrödinger's equation was giving him. The math kept producing these wave-like outputs, and Born realized the only consistent way to make sense of them was to read them as probability amplitudes. He didn't set out to revolutionize the philosophy of physics. He was just trying to make the calculations match experimental results. And they did, beautifully. But the philosophical implications were enormous, and Born himself understood that. He knew he was saying something radical, that at the most fundamental level, nature is not deterministic. You cannot predict with certainty what a single particle will do. You can only predict the odds. Now, this is where things get really interesting, because this idea, that quantum mechanics is fundamentally probabilistic, became the fault line that split the physics community for decades. And the two figures on opposite sides of that fault line were, ironically, two people who had enormous respect and affection for each other. Niels Bohr and Albert Einstein. Bohr embraced Born's interpretation. More than that, he built an entire philosophical framework around it, which became known as the Copenhagen interpretation, named after the city where Bohr's institute was located, where so much of this thinking took shape. The Copenhagen interpretation says, roughly, that the wave function is the most complete description of a quantum system that's possible. Not the most complete description we have right now, but the most complete description that can ever exist. The probabilities aren't a reflection of our ignorance. They're a reflection of reality itself. Before you measure a particle's position, it doesn't have a definite position. It's not that we don't know where it is. It's that the question, where is it, doesn't have an answer until the measurement is made. The act of measurement doesn't reveal a pre-existing fact. It creates the fact. And here's where Heisenberg comes back into the story, because in 1927, he published what might be the most famous result in all of quantum mechanics, the uncertainty principle. Heisenberg showed that there are pairs of physical quantities, position and momentum being the most famous pair, that cannot both be known precisely at the same time. And this isn't a limitation of our instruments. It's not that our rulers aren't fine enough or our clocks aren't precise enough. It's a fundamental feature of nature. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. The product of the two uncertainties can never be smaller than a tiny but definite number, roughly Planck's constant divided by 4 pi. Think about what that means in practical terms. Imagine you want to pin down exactly where an electron is. You could shine light on it. That's basically how microscopes work, right? But to locate the electron very precisely, you need light with a very short wavelength, because the wavelength sets the limit on how fine a detail you can resolve. Short wavelength means high frequency, and high frequency means high energy. Remember, energy equals h times frequency. That's Einstein's photon relation from 1905. So the very act of looking at the electron with enough precision to locate it precisely means hitting it with a high-energy photon, which kicks the electron and changes its momentum in an unpredictable way. You've pinned down the position, but you've scrambled the momentum. Try to be gentle and use a low-energy photon instead, and sure, you won't disturb the momentum much, but now your wavelength is long, and you can't locate the electron precisely. You're stuck. Not because of bad engineering, but because of the structure of reality itself. Heisenberg actually worked through this exact thought experiment. He called it the gamma-ray microscope, when he was developing the uncertainty principle. And Bohr, characteristically, argued with him about the details. Bohr thought Heisenberg's reasoning was slightly off in places, that he was relying too much on a particle picture when the wave picture was equally important. They actually had a fairly heated argument about it. Heisenberg reportedly ended up in tears at one point. These were intense, passionate debates among people who cared deeply about getting it right. But the conclusion stood. The uncertainty principle is real. It's measurable, and it's not going away. Now Einstein, and this is where the human drama really gets compelling. Einstein could not accept this, and it's important to understand why, because Einstein wasn't being stubborn or old-fashioned. He had thought more deeply about the nature of light and matter than almost anyone alive. He was the one who introduced the photon. He was the one who endorsed de Broglie's matter waves. He understood quantum mechanics at a profound level, but he believed, truly, deeply believed, that there must be a complete deterministic description of nature underneath all this probability. The wave function, he felt, was like a weather forecast, useful, statistically accurate, but not the whole story. Somewhere underneath, there had to be definite quantities with definite values, even if we couldn't see them yet. God does not play dice, he famously said, and Bohr's equally famous reply was something like, "Stop telling God what to do." The debates between Bohr and Einstein became legendary, particularly at the Solvay conferences of 1927 and 1930. These were invitation-only gatherings of the world's top physicists, held in Brussels, funded by a Belgian industrialist named Ernest Solvay. The 1927 conference is probably the most famous scientific meeting in history. The group photo alone is staggering, with 17 of the 29 attendees being or becoming Nobel laureates. And the real action happened not in the formal sessions, but at breakfast, at dinner, in the hallways. Einstein would come down to breakfast each morning with a new thought experiment, a clever scenario designed to show that the uncertainty principle could be violated, that you could, in principle, know both position and momentum simultaneously. And each time, Bohr would go away, think about it, sometimes agonize over it for hours, and come back with a refutation, showing exactly where Einstein's argument broke down, exactly how the uncertainty principle survived. One of the most beautiful examples came at the 1930 conference, where Einstein proposed what seemed like a devastating challenge. Imagine a box filled with radiation, he said. The box has a clock-controlled shutter that opens for a precisely known interval and lets out exactly one photon. You weigh the box before and after the photon escapes. Since energy has mass, via E equals mc squared, the weight difference tells you the photon's energy, and the clock tells you the exact time the photon left. So now you know both the energy and the time of emission precisely, which would violate the energy-time version of the uncertainty principle. Bohr was reportedly shaken by this one. He spent the whole evening working through it, and the story goes that he looked genuinely distressed. But by the next morning, he had found the flaw, and it was breathtakingly elegant. Bohr pointed out that when the photon leaves and the box gets lighter, the box shifts slightly in Earth's gravitational field. And here's the kicker. According to Einstein's own general theory of relativity, a clock's rate depends on its position in a gravitational field. The very act of weighing the box precisely enough to determine the photon's energy introduces an unavoidable uncertainty in the clock's rate, and therefore in the timing. The uncertainty principle holds. Einstein had been defeated by his own theory of gravity. Einstein never fully conceded. He shifted his argument over the years, moving from trying to disprove the uncertainty principle directly to arguing that quantum mechanics, while correct in its predictions, must be incomplete. There must be hidden variables, deeper quantities that we haven't discovered yet, that would restore determinism. This culminated in the famous EPR paper of 1935, Einstein, Podolsky, and Rosen, which introduced the concept of quantum entanglement and argued that it proved quantum mechanics couldn't be the full story. We'll come back to entanglement later, because it's one of the most extraordinary features of quantum mechanics, and it connects to technologies being built right now. But for the moment, what matters is this. The mainstream of physics followed Bohr, not Einstein. The Copenhagen interpretation became the working framework for quantum mechanics, and Born's probabilistic interpretation became the standard way to understand the wave function. Born won the Nobel Prize for it in 1954, almost 3 decades after his original paper, which tells you something about how long it took the community to fully digest what he'd proposed. But here's what's really remarkable about this whole period. The late 1920s, the early 1930s. While the philosophers and the giants were arguing about what quantum mechanics meant, a younger generation of physicists was already using it to do things that had never been possible before. They took Schrödinger's equation, Born's interpretation, Heisenberg's uncertainty principle, and they started applying them to real physical systems. And the results were spectacular. One of the first great triumphs was understanding the structure of atoms beyond hydrogen, the multi-electron atoms that Bohr's model had failed so badly at. And the key figure in making that work, the person who showed how quantum mechanics explains the entire periodic table of elements, was a quiet, almost pathologically shy Englishman named Paul Dirac, who was working at Cambridge and who approached quantum mechanics with a mathematical elegance that left everyone else a little bit in awe. Dirac was, by all accounts, one of the strangest and most brilliant people in the history of physics. He spoke so rarely and so precisely that his Cambridge colleagues invented a unit of measurement called the Dirac, defined as 1 word per hour. He answered questions with a literalness that bordered on the comical. There's a famous story about a lecture where someone in the audience said, "Professor Dirac, I didn't understand the equation on the top right of the blackboard." And Dirac just stood there in silence. The moderator eventually prompted him, "Aren't you going to answer the question?" And Dirac replied, "That wasn't a question. It was a statement. That's who we're dealing with. A man who thought in pure mathematical structures and who saw physics as a problem of finding the most beautiful equations, trusting that beauty and consistency would lead to truth." And in 1928, Dirac did something that still takes your breath away when you really sit with it. He was trying to solve a specific problem: how to write a quantum mechanical equation for the electron that was consistent with Einstein's special relativity. See, Schrödinger's equation worked beautifully for slow-moving particles, but it didn't account for the effects of relativity, which become important when particles move at speeds approaching the speed of light. And electrons inside atoms, especially heavy atoms with lots of protons in the nucleus pulling on them, can move fast enough that relativity matters. So Dirac set out to find a relativistic version of the wave equation for the electron, and what he found was extraordinary. The Dirac equation, as it came to be known, was elegant in a way that physicists describe almost in aesthetic terms. It naturally incorporated the electron's spin, that intrinsic angular momentum we talked about earlier, the property that makes electrons behave like tiny spinning tops, even though they're not literally spinning. In Schrödinger's framework, spin had to be added by hand, sort of bolted on as an extra feature. In Dirac's equation, it emerged automatically from the mathematics. It was just there, a necessary consequence of combining quantum mechanics with relativity. That's the kind of thing that makes physicists believe they're on the right track. When a property of nature that you had to assume before suddenly falls out of the equations on its own. But here's where it gets really wild. Dirac's equation had solutions that nobody expected. When he solved it, he found that for every solution describing an electron with positive energy, there was a corresponding solution with negative energy. Now, in classical physics, you'd just throw those away. Negative energy doesn't make physical sense, you'd say, and move on. But Dirac couldn't do that. The mathematics wouldn't let him. If you ignored the negative energy solutions, the whole framework became inconsistent. So he had to take them seriously. And what Dirac proposed was audacious. He suggested that all those negative energy states were already filled, that the vacuum of space was actually a vast sea of negative energy electrons, completely invisible to us because every state was occupied. Think of it like a concert hall where every single seat is taken. You don't notice the individual people because there are no gaps. But if one person gets up and leaves, if one negative energy electron gets knocked out of the sea, the empty seat becomes noticeable. That hole, that absence, would behave like a particle with positive energy and positive charge. It would look like an electron, but with opposite charge. Dirac initially thought this hole might be the proton, which was the only positively charged particle known at the time. But the math didn't work. The hole had to have the same mass as the electron, and protons are nearly 2,000 times heavier. So Dirac made a prediction that was genuinely shocking. There must exist a particle identical to the electron, but with positive charge, an anti-electron, a particle that no one had ever seen, that no experiment had ever detected, that Dirac was conjuring purely from the internal logic of his equation. And then, in 1932, a young American physicist named Carl Anderson was studying cosmic rays, those high-energy particles that rain down on Earth from space, using a cloud chamber at Caltech. A cloud chamber is a beautiful device, by the way. You fill a sealed chamber with supersaturated vapor, and when a charged particle flies through it, it ionizes the gas molecules along its path, and those ions act as seeds for tiny droplets of condensation. So the particle leaves a visible trail, like a tiny jet contrail, and you can photograph it. If you put the whole thing in a magnetic field, the trail curves, and the direction of the curve tells you the sign of the charge, while the tightness of the curve tells you the mass. Anderson saw tracks that curved the wrong way. They curved like an electron would, same tightness, same mass, but in the opposite direction. Positive charge. He had found Dirac's anti-electron, which he called the positron. It was the first antiparticle ever detected, and it confirmed one of the most remarkable theoretical predictions in the history of science. Dirac had predicted the existence of antimatter, an entirely new category of stuff in the universe, from pure mathematics. Think about what that means. He sat down with pen and paper, demanded that quantum mechanics and relativity be mutually consistent, and the equations told him that a previously unknown form of matter had to exist. And it did. This is one of those moments that's worth pausing on, because it tells you something deep about the nature of quantum mechanics and about physics in general. The theory wasn't just describing things we'd already observed. It was reaching ahead of experiment, telling us about parts of reality we hadn't encountered yet. That's the power of a good theory. It's not just a summary of what you know. It's a map that shows you where to look next. Now, Dirac's work was crucial for understanding atoms beyond hydrogen, but the full story of multi-electron atoms involves another key idea, and this one comes from an unlikely source. Wolfgang Pauli, remember him, the sharp-tongued critic from Vienna, proposed something in 1925 that sounds almost absurdly simple, but turns out to be one of the most consequential principles in all of physics. It's called the Pauli exclusion principle, and it says this: no two electrons in an atom can occupy the same quantum state at the same time. That's it. That's the whole rule. But let's talk about what it means, because it explains, well, basically everything about chemistry. Each electron in an atom is described by a set of quantum numbers. Think of them as an address. There's the principal quantum number, which tells you roughly how far the electron is from the nucleus, which energy level it's in. There's the angular momentum quantum number, which describes the shape of the orbital. There's the magnetic quantum number, which describes the orientation of that orbital in space. And there's the spin quantum number, which can be either up or down. Just two options. Together, these four numbers uniquely specify a quantum state. And Pauli's principle says each unique address can hold exactly one electron. No sharing, no doubling up. So what happens as you build heavier and heavier atoms? You start with hydrogen, one proton, one electron. That electron drops into the lowest energy state, the ground state, the innermost orbital. Fine. Now helium, two protons, two electrons. The second electron can still fit into that same lowest orbital because it can have the opposite spin. One electron spin up, one spin down. They have different quantum numbers, so they're in different states, and the exclusion principle is satisfied. But that orbital is now full. There's no room for a third electron at that address. So when you get to lithium, with 3 electrons, the third one can't squeeze into the innermost shell. It has to go to the next energy level out. And that changes everything about lithium's chemistry. That outer electron is farther from the nucleus, less tightly bound, easier to remove. That's why lithium is a reactive metal. It readily gives up that outer electron. Helium, with its completely filled inner shell, is a noble gas, inert, stable, chemically aloof. The difference between an explosive metal and an inert gas comes down to the Pauli exclusion principle. And this pattern repeats as you move through the periodic table. Each row corresponds to filling up a new energy level. The columns, the groups, correspond to how many electrons are in the outermost shell. Elements in the same column have similar chemistry because they have similar outer electron configurations. The entire periodic table, that beautiful chart hanging on the wall of every chemistry classroom in the world, is a consequence of quantum mechanics and the exclusion principle. Mendeleev organized the elements by their chemical properties back in 1869, and he noticed the patterns, but he had no idea why those patterns existed. Quantum mechanics explained it. The periodic table isn't just a convenient way to organize information. It's a physical consequence of how electrons obey quantum rules. Here's something else the exclusion principle explains, something you might not expect. It explains why matter is solid, why you don't fall through the floor. You might think it's because atoms are hard little balls that can't overlap, but that's not really what's going on. Atoms are mostly empty space. The nucleus is tiny compared to the electron cloud. The reason solid matter resists compression, the reason your hand stops when it hits a table, is fundamentally because of the exclusion principle. When you try to push atoms closer together, you're trying to force their electrons into the same quantum states, and the exclusion principle won't allow it. The electrons resist being squeezed into identical states, and this resistance creates what's called degeneracy pressure. It's the same pressure that keeps white dwarf stars from collapsing under their own gravity. The electrons inside the star are packed so tightly that the exclusion principle is the only thing holding the star up against the crushing weight of its own mass. So this one simple rule, no 2 electrons in the same state, gives you the structure of atoms, the periodic table, the nature of chemical bonds, the solidity of matter, and the stability of dead stars. That's an extraordinary amount of explanatory power from a single principle. And Pauli arrived at this principle not through some grand theoretical derivation, but through a painstaking study of atomic spectra, the specific wavelengths of light that atoms emit and absorb. By the early 1920s, spectroscopists had accumulated enormous amounts of data about these spectral lines, and the patterns were complicated. There were lines that should have been there according to existing models, but weren't. There were splittings and doublings that nobody could explain. Pauli stared at this data, thought about it obsessively, and realized that the patterns only made sense if you imposed this rule. 1 electron per state, no exceptions. It's worth noting that Pauli couldn't explain why the exclusion principle was true. He just showed that it had to be true for the data to make sense. The deeper explanation came later, from the connection between spin and statistics. The idea that particles with half-integer spin, like electrons, obey what are called Fermi-Dirac statistics and are fundamentally forbidden from sharing quantum states, while particles with integer spin, like photons, obey Bose-Einstein statistics, and actually prefer to pile into the same state. That distinction, fermions versus bosons, is one of the deepest divisions in the particle world, and it has consequences everywhere, from the behavior of lasers to the properties of superfluids to the structure of neutron stars. But we're getting ahead of ourselves. Let's stay in the early 1930s for a moment, because something else was happening that would transform not just physics, but the entire world. Physicists were beginning to turn their attention to the nucleus, that tiny, dense core of the atom that Rutherford had discovered, and they were about to find things in there that would change the course of human history. In 1932, the same year Anderson found the positron, James Chadwick at Cambridge discovered the neutron, the electrically neutral particle that sits alongside protons in the nucleus. And with that discovery, the modern picture of the atom snapped into focus. But more importantly, people started wondering, what holds the nucleus together? Protons are all positively charged, and positive charges repel each other. The nucleus is incredibly tiny, so those protons are packed absurdly close together. The electromagnetic repulsion between them is enormous. There must be some other force, something much stronger than electromagnetism, but acting only at very short range, that glues the nucleus together. And understanding that force, the strong nuclear force, would require quantum mechanics in ways that nobody had quite imagined yet. Because here's the thing, electromagnetism, the force we'd understood best since Maxwell's equations in the 1860s, has infinite range. It gets weaker with distance, sure, but it never truly disappears. Two charged particles on opposite sides of the universe still feel each other's pull, at least in principle. But whatever was holding the nucleus together had to be fundamentally different. It had to be incredibly powerful, strong enough to overpower the ferocious electromagnetic repulsion between protons crammed into a space about a femtometer across. That's a millionth of a billionth of a millimeter. And yet, it had to essentially vanish just a tiny bit beyond the edge of the nucleus. Step even a little outside that boundary, and the force drops to practically nothing. That's a strange kind of force. Nothing in classical physics behaved quite like that. The person who made the first real theoretical breakthrough on this was a young Japanese physicist named Hideki Yukawa. And his story is worth lingering on because it illustrates something beautiful about how quantum mechanics was changing the way physicists thought about forces themselves. Yukawa was working at Osaka University in the mid-1930s, relatively isolated from the great European physics centers. Japan had a growing physics community. Yoshio Nishina had studied with Bohr in Copenhagen and brought quantum mechanics back to Japan. But Yukawa was still something of an outsider to the main currents of the field. He was quiet, thoughtful, the kind of person who would sit with a problem for months. And the problem he was sitting with was exactly this one. What mediates the strong force between nucleons, protons and neutrons, inside the nucleus? Now, here's where the story connects back to something we talked about earlier, the way quantum mechanics had already transformed our understanding of electromagnetism. By the early 1930s, physicists were developing what would eventually become quantum electrodynamics, QED, the quantum theory of how charged particles interact with electromagnetic fields. And one of the key insights was that electromagnetic forces could be understood as being carried by particles, specifically photons. When two electrons repel each other, you can think of it as one electron emitting a virtual photon and the other absorbing it. The exchange of that photon is what creates the force. It's a strange picture, honestly. Forces aren't just mysterious pushes and pulls. They're the result of particles being tossed back and forth, like two people on ice skates, throwing a ball between them and getting pushed apart by the recoil. The analogy isn't perfect, but it gives you the flavor. Yukawa took this idea and ran with it. If electromagnetism is mediated by the exchange of photons, then maybe the strong nuclear force is mediated by the exchange of some other particle, a particle nobody had discovered yet. And here's where his reasoning got really clever. Photons are massless, and that's connected to the infinite range of electromagnetism. There's a relationship in quantum field theory between the mass of the carrier particle and the range of the force it mediates. A massless carrier gives you infinite range, but if the carrier particle has mass, the force has a finite range, and the heavier the carrier, the shorter the range. So Yukawa worked backward from what was known about the strong force's range, roughly 1 to 2 femtometers, and calculated what the mass of this hypothetical carrier particle would need to be. He published his prediction in 1935. The particle should have a mass somewhere around 200 times the mass of an electron, roughly a tenth the mass of a proton. Something intermediate between the electron and the proton, and that's actually where the name meson comes from. Meso meaning middle, a particle of middle mass. Yukawa called it a heavy quantum in his original paper, but the term meson stuck. At the time, no such particle was known to exist. It was a pure prediction, pulled from the logic of quantum mechanics and the observed properties of nuclear forces. Think about what a leap that was. A relatively unknown physicist in Osaka, working from theoretical principles, predicting the existence of a particle that nobody had ever seen, based on the quantum mechanical insight that forces are mediated by particle exchange. It's the kind of thing that makes you appreciate how powerful the framework of quantum mechanics had become by the mid-1930s. It wasn't just describing atoms anymore. It was telling you what new particles should exist. Now, the experimental story that followed was messy, as experimental stories often are. In 1936, Carl Anderson, the same Anderson who found the positron, and Seth Nettermeyer discovered a new particle in cosmic rays that had roughly the right mass. Everyone got excited. Yukawa's particle found. But something was off. This particle didn't interact strongly with nuclei the way Yukawa's meson was supposed to. It passed right through matter almost as easily as a neutrino. If this was supposed to be the carrier of the strong nuclear force, it was doing a terrible job of it. The puzzle persisted for about a decade, and it wasn't resolved until the late 1940s, when a team in Bristol, led by Cecil Powell, used photographic emulsions flown at high altitudes to capture cosmic ray interactions. They found that there were actually two different particles. The one Anderson had found, now called the muon, was not Yukawa's particle at all. It was something else entirely, a heavier cousin of the electron with no strong nuclear interactions. The actual Yukawa particle was the pion, which Powell's group identified in 1947. The pion was produced in cosmic ray collisions, and it decayed quickly into muons, which is why Anderson had seen muons but missed the pions. This whole episode is a wonderful example of how science actually works. The prediction was right, but the experimental confirmation took a winding path through a case of mistaken identity. Yukawa received the Nobel Prize in 1949, the first Japanese physicist to be so honored. Powell got his in 1950. And the muon, that unexpected interloper, prompted the physicist I. Rabi to ask his famous question, who ordered that? Because the muon didn't seem to fit into any tidy scheme. It was just like an electron, only heavier. Why should such a particle exist? That question, in a way, is still being asked. The muon was the first hint that the particle zoo was going to be a lot more crowded and a lot more confusing than anyone had hoped. But let's come back to the strong force and what Yukawa's work meant for the bigger picture. The idea that forces are mediated by particle exchange, what physicists call the exchange force model, became one of the central organizing principles of 20th century physics. It's the conceptual backbone of what would eventually become the standard model of particle physics, which we'll get to. Every fundamental force in nature, with the stubborn exception of gravity, would eventually be understood in terms of carrier particles being exchanged between matter particles. Electromagnetism has the photon. The strong force, in its deeper modern form, has particles called gluons. The weak nuclear force, the one responsible for certain kinds of radioactive decay, has the W and Z bosons. All of this grew from the seed that Yukawa planted. And speaking of the weak force, that's another thread worth pulling on, because it's deeply quantum mechanical, and it led to some of the most surprising discoveries of the 20th century. The weak nuclear force was actually the first of the nuclear forces to be theorized, in a sense. Back in 1933, Enrico Fermi, one of the great physicists of the century, a man equally gifted in theory and experiment, which is rare, proposed a theory of beta decay, the process where a neutron inside a nucleus transforms into a proton while emitting an electron and a ghostly particle called a neutrino. Fermi's theory was inspired by quantum electrodynamics. He modeled beta decay as a point interaction, 4 particles meeting at a single point in spacetime, and it worked remarkably well for predicting decay rates and energy spectra. But it was clear even then that this couldn't be the final word, because Fermi's theory had mathematical problems at high energies. It predicted probabilities greater than 1, which is physically nonsensical. The resolution would take decades and would involve some of the most brilliant and tortured theoretical work in physics history. But the key point for our story is this: the weak force, like the strong force, would eventually be understood as mediated by particle exchange, specifically by very heavy particles called the W and Z bosons, which weren't discovered experimentally until 1983 at CERN. Their enormous mass, about 80 to 90 times the mass of a proton, is what makes the weak force so short-ranged and, well, weak. Remember Yukawa's insight. Heavier carrier means shorter range. The W and Z bosons are so heavy that the weak force barely reaches across the width of a single proton. But here's what's really remarkable. In the 1960s and early 1970s, physicists, particularly Sheldon Glashow, Abdus Salam, and Steven Weinberg, working somewhat independently, showed that the weak force and electromagnetism are actually the same force. At very high energies, the kind of energies that existed in the first moments after the Big Bang, there's no distinction between them. They're 2 faces of a single electro-weak force. The difference we see at everyday energies is a consequence of something called symmetry breaking. The idea that the underlying laws of physics have a symmetry that the actual state of the universe doesn't display. It's like a ball sitting on top of a perfectly symmetrical hill. The hill is symmetric, but the ball has to roll down one side or the other, breaking the symmetry. In the case of the electroweak force, the symmetry breaking is what gives the W and Z bosons their enormous mass while leaving the photon massless. And the mechanism responsible for that, the Higgs mechanism, predicted the existence of yet another particle, the Higgs boson, which wasn't confirmed until 2012 at the Large Hadron Collider. Think about the arc of that story for a moment. Planck introduces quantization in 1900 to solve the blackbody problem. 35 years later, Yukawa uses the quantum idea of particle exchange to predict a new particle mediating the strong force. Another 30 years after that, theorists unify two of the four fundamental forces using quantum field theory. And another 40 years after that, the particle predicted by the unification, the Higgs boson, is found. Over a century of quantum thinking, each generation building on the last, each breakthrough opening up new questions, and the strong force had its own deepening story. Yukawa's pions turned out not to be fundamental particles. Starting in the 1950s and accelerating through the 1960s, particle accelerators, machines that slam particles together at enormous energies to see what comes out, began discovering a bewildering zoo of strongly interacting particles. Hundreds of them. Particles called kaons, sigmas, lambdas, deltas, omegas, psi particles. It was chaos. There were so many that physicists started calling it the particle zoo, and not affectionately. Willis Lamb, in his Nobel lecture in 1955, joked that the Nobel Prize in Physics should be awarded to whoever did not discover a new particle that year. Something had to be organizing all of this, some deeper structure beneath the zoo. The breakthrough came from Murray Gell-Mann and, independently, George Zweig in 1964. They proposed that all these strongly interacting particles, the hadrons, were made of smaller, more fundamental constituents. Gell-Mann called them quarks, borrowing the word from a line in James Joyce's Finnegan's Wake, 3 quarks for muster mark. Zweig called them aces, but Gell-Mann's name won out. The idea was that protons, neutrons, pions, and all those other particles in the zoo were just different combinations of a small number of quark types. A proton is 2 up quarks and 1 down quark. A neutron is 1 up quark and 2 down quarks. A pion is a quark and an antiquark. Suddenly the zoo had a taxonomy. Hundreds of particles could be explained by combining just a handful of building blocks. But quarks had a problem. Nobody had ever seen one in isolation. You could smash protons apart as hard as you liked, and you'd never find a free quark flying out. This was deeply puzzling, and led many physicists to wonder whether quarks were real, physical entities or just mathematical bookkeeping devices. The resolution came from the development of quantum chromodynamics, QCD, the quantum field theory of the strong force, which matured through the late 1960s and 1970s. In QCD, quarks carry a type of charge called color charge, analogous to electric charge, but coming in 3 varieties, whimsically named red, green, and blue. The force between quarks is mediated not by pions. Those are a secondary effect, but by massless particles called gluons. And gluons themselves carry color charge, which makes the strong force behave in a way that's completely unlike electromagnetism. In electromagnetism, the force between charges gets weaker as you pull them apart. In QCD, the force between quarks gets stronger as you pull them apart. It's like a rubber band. Stretch it and it pulls back harder. This property, called confinement, is why you never see a free quark. Try to pull one out of a proton, and the energy you put in eventually creates new quark-antiquark pairs, which combine into new hadrons. You always end up with bound combinations, never isolated quarks. And yet, at very short distances, when quarks are very close together, inside a proton, the strong force actually gets weaker. This counterintuitive property is called asymptotic freedom, and it was discovered by David Gross, Frank Wilczek, and David Politzer in 1973. It was a stunning result because it meant that at high enough energies, quarks behave almost as if they're free particles, which explained the results of deep inelastic scattering experiments at Stanford in the late 1960s, where electrons fired at protons bounced off as if they were hitting small, hard, point-like objects inside. Those objects were quarks, behaving as nearly free particles because at those short distances, the strong force loosens its grip. So by the mid-1970s, a grand picture was coming together. All known matter is made of quarks and leptons. Leptons being particles like electrons, muons, and neutrinos that don't feel the strong force. All forces except gravity are mediated by carrier particles, photons, gluons, W and Z bosons. The mathematical framework underlying all of this is quantum field theory, the marriage of quantum mechanics and special relativity. And the whole package, the particles, the forces, the symmetries, is what we call the standard model of particle physics. It's one of the most successful scientific theories ever constructed. Its predictions have been confirmed to extraordinary precision, sometimes agreeing with experiment to 10 or 12 decimal places. And every single piece of it grew from the seed that Planck planted in 1900, from the strange, unsettling idea that energy comes in lumps. But the standard model, for all its triumphs, leaves some enormous questions unanswered. And one of the deepest goes all the way back to that argument between Bohr and Einstein. The question of what quantum mechanics actually means, what's really happening when you're not looking, and whether the universe is as strange as the math seems to suggest. Because in the decades after the Bohr-Einstein debates, most physicists adopted a pragmatic attitude. Shut up and calculate. The Copenhagen interpretation worked, predictions matched experiments, and worrying about what it all meant was considered a bit, well, philosophical, not real physics. But not everyone was willing to let it go. And in 1964, a quiet Irish physicist working at CERN named John Bell decided to do something about it. Bell wasn't a famous figure. He wasn't a Nobel laureate. He spent most of his career working on particle physics accelerator design, the practical engineering side of things, not the glamorous theoretical frontier. But in his spare time, in the margins of his real job, he thought about the foundations of quantum mechanics, the questions most of his colleagues considered settled or, worse, irrelevant. And what he figured out in 1964 might be the most profound result in all of physics. It's certainly one of the most beautiful, and it starts, as so many things do, with Einstein. Remember the EPR paper from 1935? Einstein, Podolsky, and Rosen argued that quantum mechanics must be incomplete. Their reasoning went like this. If you have two particles that are entangled, correlated in that peculiar quantum way, then measuring one particle instantly tells you something about the other, no matter how far apart they are. Quantum mechanics says neither particle has a definite state until you measure it. But Einstein found that absurd. His intuition, and it's a perfectly reasonable intuition, was that the particles must have had definite properties all along. We just didn't know what those properties were. There must be some deeper layer of reality, some set of hidden variables that quantum mechanics doesn't capture. The theory works, sure, but it's like a weather forecast that gets the temperature right without actually understanding atmospheric physics. It's a useful shorthand, not the full story. And for nearly 30 years, that's where things sat. Most physicists shrugged and said, well, maybe there are hidden variables, maybe there aren't. But either way, the predictions are the same. So who cares? It seemed like a purely philosophical question, the kind of thing you could argue about over beer, but never actually test. John Bell showed that you could test it. Here's the thing that makes Bell's theorem so remarkable. He didn't build an experiment. He didn't need a laboratory. He sat down with a pencil and paper and proved, mathematically, that Einstein's hidden variable idea and standard Quantum mechanics actually make different predictions, not in some exotic, unreachable scenario, but in a straightforward experiment you could actually do. The two views of reality, Einstein's common sense version where particles have definite properties all along, and quantum mechanics version where they don't, lead to measurably different outcomes. And that means you can let nature settle the argument. Let me try to give you the flavor of how this works, because it's genuinely beautiful, and you don't need advanced math to follow the logic. Imagine you have a source that produces pairs of entangled particles, let's say photons, and sends one to Alice and one to Bob. Alice and Bob are far apart, maybe across a room, maybe across a city. Each of them has a detector that can measure their photon's polarization, and each of them can choose to orient their detector at different angles. They make their measurements independently, without communicating, and then later, they compare their results. Now, if Einstein was right, if each photon carries a hidden instruction set that determines in advance how it will behave at any detector angle, then there's a limit to how correlated Alice and Bob's results can be. Bell worked out this limit precisely. It's an inequality, a mathematical bound. If hidden variables are the explanation, then a certain combination of correlations between Alice and Bob's measurements can never exceed a specific number. It's like saying, if the particles are just carrying pre-programmed answers, there's only so much agreement they can show, no matter how cleverly the programs are written. But quantum mechanics predicts that the correlations can exceed that bound, not by a tiny amount either. Quantum mechanics says the correlations can be noticeably stronger than anything hidden variables allow. And that's Bell's inequality. If you do the experiment and the correlations stay within the bound, Einstein was right and quantum mechanics is incomplete. If the correlations exceed the bound, then no hidden variable theory of the kind Einstein imagined can explain what's happening. The universe really is as strange as quantum mechanics says. Think about what that means for a second. This isn't about interpretation anymore. This isn't philosophy. It's a concrete, experimental question with a yes or no answer. And Bell published this result in 1964 in a paper that appeared in a short-lived and fairly obscure journal called Physics Physique Physica. It didn't get a lot of attention at first. Most physicists were busy with quarks and the particle zoo and didn't think much about foundations. But a few people noticed, and they started trying to do the experiment. The first serious attempt came from John Clauser, a young American physicist who read Bell's paper as a graduate student and became obsessed with it. Clauser actually had trouble finding an advisor who would support the work. Testing Bell's inequality was considered a career risk, a waste of time, a detour into philosophy. But Clauser was stubborn. In 1972, together with Stuart Friedman at Berkeley, he performed the first real test. They used pairs of entangled photons produced by exciting calcium atoms, measured polarization correlations at different angles, and compared the results to Bell's inequality. The correlations violated the inequality. Quantum mechanics won. But the experiment wasn't perfect. There were loopholes, technical gaps that a determined skeptic could point to. The biggest one was the locality loophole. In Clauser and Friedman's setup, the detector settings were chosen in advance, before the photons were emitted. So in principle, some unknown signal could have traveled between the detectors, or from the source to the detectors, coordinating the results. It was far-fetched, but physics is a discipline that takes far-fetched possibilities seriously when the stakes are this high. This is where Alain Aspect enters the story. Aspect was a French physicist at the University of Paris-Sud in Orsay, and in the early 1980s, he designed a much more sophisticated version of the experiment. His key innovation was switching the detector settings while the photons were already in flight. The idea is elegant. If you don't decide which angle to measure until after the photons have left the source, then there's no way any signal traveling at the speed of light or slower could carry information between the detectors in time to fake the correlations. You're closing the locality loophole. Aspect's experiments, performed in 1981 and 1982, were landmark results. The correlations violated Bell's inequality by 5 standard deviations, a clear, unambiguous signal, and the rapid switching of detector settings made the locality loophole much harder to invoke. The universe, it seemed, really was non-local in some deep sense. Einstein's dream of a common-sense reality underlying quantum mechanics was in serious trouble. But here's what's really important to understand, and it's a point that trips people up all the time. When physicists say quantum mechanics is non-local, they don't mean you can use entanglement to send messages faster than light. You can't. When Alice measures her photon, she gets a random result, completely random. She can't control what she gets, and she can't encode any information in it. It's only when Alice and Bob later compare their results that the spooky correlations become visible. The correlations are non-local, but the information isn't. It's as if the universe has a rule that says, the outcomes will be coordinated in ways that no local hidden mechanism can explain, but I won't let you exploit that coordination to actually communicate. Nature protects causality, even while violating our intuitions about locality. And over the decades since Aspect's experiments, the tests have gotten better and better. In 2015, a team at Delft University of Technology in the Netherlands, led by Ronald Hansen, performed what's often called the first loophole-free Bell test. They closed the locality loophole and the detection loophole simultaneously, using entangled electrons in nitrogen vacancy centers in diamond, separated by over a kilometer. The result? Bell's inequality was violated again. And in 2022, the Nobel Prize in Physics was awarded to John Clauser, Alan Aspect, and Anton Zeilinger. Zeilinger being an Austrian physicist who had extended Bell test experiments in numerous creative directions for their work on entangled photons and the violation of Bell inequalities. It took nearly 60 years from Bell's paper to the Nobel, but the physics community finally acknowledged that these foundational questions weren't just philosophy. They were among the most important experiments ever performed. So where does this leave us? It tells us something genuinely deep about the nature of reality. It tells us that the universe does not work the way Einstein hoped. There is no hidden layer of predetermined answers that explains quantum correlations. The randomness and the entanglement are fundamental. When two particles are entangled, they are not two separate things carrying coordinated instructions. They are, in some sense that's hard to put into everyday language, one thing, described by one quantum state, even when they're separated by enormous distances. And this isn't just a philosophical curiosity anymore. Entanglement has become a practical resource. It's the foundation of quantum computing, where entangled qubits can explore vast computational spaces simultaneously. It's the basis of quantum cryptography, where any attempt to eavesdrop on an entangled communication channel disturbs the correlations in a detectable way. Nature itself becomes your security guard. And it's central to quantum teleportation, which isn't teleportation in the science fiction sense. You're not beaming matter anywhere, but rather the transfer of a quantum state from one particle to another using entanglement and classical communication. Zeilinger's group demonstrated quantum teleportation across the Danube River in Vienna in 2004, and Chinese researchers have since teleported quantum states to a satellite in orbit. But even with all these practical applications blooming, the interpretive questions haven't gone away. In fact, they've multiplied. Because Bell's theorem killed one particular class of hidden variable theories, the local ones, the ones Einstein would have liked. But it didn't tell us which interpretation of quantum mechanics is correct. Copenhagen says the wave function collapses when you measure. Many Worlds says it never collapses, and instead, every possible outcome happens in a branching universe. Pilot wave theory, originally proposed by de Broglie and later developed by David Bohm, says particles have definite positions at all times but are guided by a real physical wave, and this theory is explicitly non-local, which Bell's theorem actually permits. There are other interpretations too: decoherence-based approaches, relational interpretations, cubism, which treats quantum probabilities as personal beliefs of the agent making the measurement. And here's the thing that might surprise you. As of right now, today, there is no consensus. Physicists do not agree on what quantum mechanics means. They agree on the math. They agree on the predictions. They agree on what the experiments show. But they do not agree on what is actually happening. Is the wave function a real thing out there in the world? Or is it just a tool for calculating probabilities? Does measurement create reality, or reveal it, or split it? These are open questions, genuinely open, and some of the smartest people alive disagree about the answers, which brings us to something that might seem surprising, given everything we've talked about: all the particles, the forces, the symmetries, the extraordinary precision of the Standard Model. Because for all its success, quantum mechanics has one glaring, almost embarrassing gap. It doesn't include gravity. The Standard Model describes 3 of the 4 fundamental forces beautifully, but gravity, the force you feel right now, the force keeping you in your bed, the force that shapes galaxies and bends light itself, just refuses to fit inside the quantum framework. And that's not a minor omission. That's enormous. Think about what it means. We have a theory that explains how atoms work, how light behaves, how particles interact, how stars burn, how your phone's processor switches transistors on and off billions of times a second. And then we have another theory, general relativity, Einstein's masterwork from 1915, that explains how gravity works, how massive objects curve the fabric of space-time, how planets orbit, how black holes form, how the universe itself expands. Both theories are spectacularly successful. Both have been tested to extraordinary precision, and they are, as far as anyone can tell, fundamentally incompatible. Here's why that's such a deep problem. In general relativity, space-time is smooth. It's a continuous, flexible fabric. Mass and energy tell space-time how to curve, and curved space-time tells matter how to move. That's the beautiful geometric picture Einstein gave us. But in quantum mechanics, everything is grainy. Energy comes in packets. Fields fluctuate. At tiny enough scales, things get jittery and uncertain. The Heisenberg uncertainty principle says you can't pin down both position and momentum simultaneously, and that uncertainty doesn't go away. It's baked into reality. So what happens when you try to apply quantum rules to gravity? What happens when you zoom in on space-time itself, down to unimaginably small scales? The scale we're talking about has a name. It's called the Planck length, and it's about 10 to the minus 35 meters. That's so small it makes a proton look like a galaxy. At that scale, Quantum fluctuations should be so violent that space-time itself becomes turbulent, foamy, chaotic, maybe not even meaningful as a smooth surface anymore. John Wheeler, the same physicist who coined the term black hole, called this quantum foam. And the problem is, we have no tested theory that describes what happens there. General relativity breaks down. The equations give infinities. And not the kind of infinities you can tidy up with renormalization, the way physicists learn to handle infinities in quantum electrodynamics. Gravity is what physicists call non-renormalizable. The infinities just keep getting worse the harder you try to fix them. This isn't a new realization, by the way. People have known about this tension since at least the 1930s. Physicists tried to quantize gravity the same way they quantized electromagnetism, by imagining a force-carrying particle for gravity called the graviton, analogous to the photon. And on paper, a graviton makes sense in some ways. It would be massless. It would travel at the speed of light. It would have a spin of 2. You can write down the beginning of a quantum theory of gravity using gravitons. But when you try to calculate anything beyond the simplest interactions, the math explodes. Every correction you add makes the infinities worse. It's like trying to balance an ever-growing tower of blocks on a single point. Each new level makes the whole thing more unstable. So for decades, this has been the great unsolved problem in fundamental physics. How do you reconcile quantum mechanics with general relativity? How do you build a theory of quantum gravity? Now, there have been serious attempts, and the two most prominent ones are string theory and loop quantum gravity. Let's talk about string theory first, because it's probably the one you've heard of, and its story is genuinely strange. String theory didn't start as a theory of quantum gravity at all. It started in the late 1960s as an attempt to explain the strong nuclear force, the force that holds quarks together inside protons and neutrons. A young Italian physicist named Gabriele Veneziano was trying to find a mathematical formula that described how strongly interacting particles scatter off each other. And in 1968, he stumbled on something remarkable. He found that an obscure mathematical function written down by Leonhard Euler 2 centuries earlier, the Euler beta function, fit the experimental data surprisingly well. But nobody knew why. It was a formula without a physical picture behind it. Then, in 1970, Yoichiro Nambu, Holger Beck-Nielsen, and Leonard Susskind independently realized what the formula was secretly describing. It was describing tiny, one-dimensional vibrating strings. Not particles, strings, little loops or filaments of energy, vibrating at different frequencies. And just like a guitar string can vibrate in different modes to produce different musical notes, these fundamental strings would vibrate in different modes to produce different particles. One vibration pattern gives you a photon, another gives you an electron, another gives you a quark. It was an extraordinarily elegant idea. All the diversity of the particle zoo, explained by a single kind of object vibrating in different ways. But there was a problem. Actually, several problems. The original string theory predicted a particle that nobody had ever seen, a massless particle with spin 2. At first, this seemed like a flaw, but then people realized something astonishing. A massless spin 2 particle is exactly what a graviton would be. String theory wasn't just a theory of the strong force. It naturally, almost accidentally, included gravity. It was producing quantum gravity as a byproduct, without even trying. This was a huge deal. For the first time, there was a framework where gravity and quantum mechanics seemed to coexist without the usual catastrophic infinities. The extended nature of the string, the fact that it wasn't a point particle, but had a tiny length, acted as a natural smoothing mechanism. It softened the calculations at very short distances, taming the infinities that had plagued every previous attempt to quantize gravity. But string theory demanded something strange. For the math to work consistently, the strings couldn't vibrate in just 3 dimensions of space. They needed more. The original version required 26 dimensions. Later, more sophisticated versions, superstring theories, which incorporated supersymmetry, a proposed symmetry between fermions and bosons, brought that number down to 10. 10 dimensions of space-time, 9 of space, 1 of time. And since we obviously only experience 3 spatial dimensions in everyday life, the extra 6 had to be hidden somehow. The proposal was that they're curled up, compactified, rolled into tiny shapes so small we can't detect them. Imagine an ant walking on a garden hose. From far away, the hose looks like a one-dimensional line, but up close, the ant can walk around the circumference. There's a hidden circular dimension. String theory says something similar is happening with 6 extra dimensions, curled up at the Planck scale. Now, this is either beautiful or deeply troubling, depending on your perspective. The mathematics of string theory is extraordinarily rich. It's produced genuine insights in pure mathematics. It's led to powerful tools for thinking about black holes. In 1996, Andrew Schrödinger and Qumran Vafa used string theory to derive the entropy of a certain type of black hole, matching a prediction Stephen Hawking had made 20 years earlier using very different methods. That was a stunning result. It suggested that string theory was capturing something real about quantum gravity. But here's the thing that makes a lot of physicists uncomfortable. String theory, as of today, has made no testable predictions that we can verify with current or foreseeable experiments. The energy scales where stringy effects would become visible are so far beyond what any particle accelerator can reach that direct experimental tests seem practically impossible. And the theory has an enormous landscape of possible solutions. Estimates range from 10 to the 500 different possible configurations of those extra dimensions, each giving rise to a different version of low-energy physics. Some critics argue that a theory that can accommodate almost anything predicts almost nothing. Others counter that the theory is still being developed, that we don't yet understand it well enough to know what it truly predicts. The other major approach to quantum gravity is loop quantum gravity, and it takes a very different philosophy. Instead of starting with particles and strings and adding gravity, loop quantum gravity starts with general relativity and tries to quantize it directly. The key figures here are Abhay Ashtekar, Lee Smolin, and Carlo Rovelli, working from the mid-1980s onward. What Ashtekar did in 1986 was reformulate general relativity in a new set of variables, connection variables, similar to the ones used in gauge theories like the Standard Model. And when Smolin and Rovelli applied quantum rules to this reformulated version of gravity, something remarkable emerged. Space itself turned out to be quantized, not smooth, not continuous, but made of discrete chunks. The geometry of space at the Planck scale has a granular structure, tiny, indivisible units of volume and area woven together in a network that physicists call a spin network. Think about that for a second. In loop quantum gravity, space isn't a stage on which physics happens. Space is itself a quantum entity, made of finite pieces, subject to uncertainty and fluctuation. There's a smallest possible volume, roughly a Planck length cubed, and you can't subdivide it further. It's like discovering that what you thought was a smooth sheet of fabric is actually a very fine mesh woven from tiny threads. And those threads, the edges and nodes of the spin network, are the fundamental building blocks of space. Loop quantum gravity has its own successes and its own open problems. One of its most celebrated results is in cosmology. When you run the equations of loop quantum gravity backward in time, toward the Big Bang, you don't hit a singularity, that terrifying point of infinite density and curvature that general relativity predicts. Instead, the quantum effects of gravity create a repulsive force at extreme densities, and the universe bounces. The Big Bang becomes a big bounce. The universe may have existed before, contracted, reached a minimum size, and then expanded again. It's a beautiful result, though it remains theoretical. We don't yet have observational evidence to confirm or deny it. And this is where we are, right now, tonight. Two major frameworks for quantum gravity, each with profound insights, each incomplete, each lacking direct experimental confirmation. There are other approaches too. Causal set theory, which proposes that space-time is fundamentally a discrete set of points with causal relationships between them. There's the holographic principle, inspired by black hole physics, which suggests that all the information in a three-dimensional region of space can be encoded on its two-dimensional boundary, like a hologram. That idea, developed by Gerard 't Hooft and Leonard Susskind, led to Juan Maldaceno's remarkable ADS/CFT correspondence in 1997, which establishes a precise mathematical equivalence between a gravitational theory in a curved space-time and a quantum field theory without gravity on its boundary. It's one of the most influential results in theoretical physics in the last 30 years, and it hints that space-time itself might be an emergent phenomenon, something that arises from more fundamental quantum information. And maybe that's the deepest lesson of this whole journey we've been on tonight. From Planck's reluctant quantization of energy in 1900, through Einstein's photons and Bohr's orbits, through the wild creativity of Heisenberg and Schrödinger and Dirac, through the strange implications of entanglement and Bell's theorem, through the extraordinary architecture of the Standard Model, through all of it, the pattern has been the same. Every time physicists thought they understood what reality was made of, they discovered another layer. Every time they built a framework that seemed complete, nature revealed something that didn't fit. And every time, the resolution required not just new equations, but a new way of thinking about what the equations meant. Quantum mechanics started as a desperate mathematical trick to fix a problem with thermal radiation. It became the most successful theory in the history of science. It tells us that the world is not what it seems, that certainty is an illusion, that particles are not really particles, that measurement is not passive observation, but active participation, that two entangled photons separated by the width of the universe remain connected in ways that defy our everyday intuition about space and separation. And yet, for all its strangeness, it works. It works so well that every piece of modern technology, every laser, every semiconductor, every MRI machine, every LED, every fiber optic cable carrying your voice across oceans, is built on its principles. So as you lie there, settling deeper into your pillow, here's something worth holding gently in your mind. The universe, at its most fundamental level, is not a machine made of tiny billiard balls following predictable paths. It's something more subtle than that. Something stranger, and honestly, something more wonderful. It's a place where probability is woven into the fabric of reality, where the act of looking changes what you find, where particles can be in two places at once until the moment they're not. And nobody, not Einstein, not Bohr, not Feynman, not anyone alive today, fully understands why. Feynman himself said it plainly. I think I can safely say that nobody understands quantum mechanics, and he meant it as a statement of honesty, not defeat. But that's okay. That's more than okay. Because the not knowing is where the next discovery lives. Somewhere out there. Maybe in a quiet office. Maybe in a late-night conversation between two young physicists who haven't yet realized they're about to change everything. Someone is turning over an idea that will make the next piece fall into place. The story isn't over. It's never been over. And that, maybe, is the most comforting thought of all. That the universe still has secrets. That there are still deep, beautiful, important things left to figure out. And that the same curiosity that kept Planck up late in 1900, staring at his equations, wondering what they meant, that same curiosity is still alive, still burning, still asking the next question. Let that thought settle. Let it be soft and quiet, like the hum of something far away. The quantum world is strange, and it is real, and it is yours. Every atom in your body is a quantum system. Every breath you take is a symphony of quantum interactions. Every star you've ever seen is burning because of quantum tunneling in its core. You are made of this strangeness. You are part of it. And tonight, you don't need to solve any of it. You just need to rest. So let the questions drift. Let the particles do whatever they do when no one's watching. And let yourself gently, quietly, fall asleep.